So good morning class 9th, myself KG Misra, and today we will starting the chapter motion, the first chapter of physics. So before going to the topics of motion, we need to know certain things. And first thing which we need to know, that is physical quantity. Physical quantity. Now question comes, what is actually physical quantity is? What the physical quantity is? So straight away, first write the definition of this. The quantities which can be measured are called physical quantities. The quantities which can be measured are called physical quantities. Full stop. For example, length, time, mass, force, weight, electric current, etc. These are the physical quantities. So whatever you can measure, that is called physical quantity. Can you measure the area? Obviously you can measure the area, because you know the area is length into width for a rectangle. Area is side square for a square, so you can measure the area. You can measure the height of your classmates, so obviously you can measure it, so it's a physical quantity. You can measure the time, you can measure the force, okay, you can measure the current, because you will take the charger of your mobile phone or your papa's mobile phone, you will find it's written 1 ampere or 1.5 ampere or 2 ampere, whatever it is written over there. So we can measure it, that's why it is written over here. Without measuring, how can we find? What cannot be measured? Yes. Whatever you feel, can we measure it? If someone is angry, can we say that it is angry this much amount? 10 units or 20 units? Someone is angry more, that is 50 units? Can we say that? No, because it cannot be measured. So what you feel, that cannot be measured. But here these things can be measured, and these are called physical quantities. Now these physical quantities are divided into two parts. First is, that is called scalar quantities. S-C-A-L-E-R, scalar quantities. What are scalar quantities? And second is vector quantities. What are vector quantities now? See, out of these physical quantities, no, those quantities which have, please write the definition. The physical quantities which have only magnitude but no direction. The physical quantities which have only magnitude but no direction and follows the rules of arithmetic are called scalar quantities. For example, length, time, mass, electric current. These two will not be there. Okay, so examples are length, time, mass, electric current, etc. These are the scalar quantities. Now the question comes, what is magnitude? Because see, I have used these words. No? First I have used that is the quantities which have magnitude plus only magnitude, okay, no direction. So what is magnitude actually? Magnitude is actually nothing but it is a number plus unit. Now what is number and what is unit? What does it mean? Suppose you like this suppose kheer very much, and a day your mama was very happy from you because you studied very well and your mama was happy and she told, okay, I'm going to prepare kheer for you, but you get some sugar from the shop, from the nearest shopkeeper, and you went to the shop and you bought asked for the sugar, and shopkeeper asked you how much sugar you want. You told, I want 2 kg of sugar. So what is this 2? 2 is a number. And what is a kg? Kg is a unit. And when both combine together, it becomes magnitude. So the physical quantities which have only magnitude but no direction. Like see, when you are talking about the height, so you say my height is 5 feet so 7 inches. My height is 5 feet 3 inches. Okay. So you never mention any direction or anything else. You mention number and you mention unit. So that is the scalar quantity. When it is we are talking about the mass, you say, yes, my mass is 50 kg. So this is the only magnitude you are talking about, number and the unit. In the same way, the time. Someone asks you about time, you say, okay, I will coming after 3 hours. So 3 and hour. That's the number and unit, magnitude. So scalar quantities are those quantities which have only magnitude and direction. Magnitude, no direction. Okay. Scalar quantities don't have direction, only magnitude. Now, what about the vector? One more thing about it. If we are having suppose we are talking about the sugar only, okay, and the same day you brought 2 kg of sugar and your father brought 5 kg of sugar. So what is the total mass of the sugar present at your home? That is 7 kg of sugar. How you got it? 5 plus 2. You have used the simple algebra. So wherever you can use the simple algebra to add, that is called scalar quantity. Okay. Now, what about what are vector quantities? First, write down the definition. The physical quantities which have magnitude as well as direction and follows vector algebra are called vector quantities. For example, force, weight, acceleration, velocity, displacement, etc. So force, weight, acceleration, velocity, displacement, etc. These are the vector quantities which have magnitude and direction. Now, how can we say that it has got the magnitude and direction both? Very nice. Suppose we know already, the force has got the unit Newton. And suppose a cart is coming from this side. Okay, cart, the fruit sellers used to keep their fruit and sell on the market. Suppose that cart someone has pushed from that side and it is approaching towards you with a speed of 20 meters per second. And you applied a force of 4 Newton from this side. It is coming from that side and you apply force from this side. So the cart is moving in this direction with a speed of 20 meter per second, and you apply this 4 Newton force in the opposite direction. What you will find? What will happen to the cart? Will its speed increase or decrease? Obviously, you are applying force in opposite direction, so its speed is going to decrease. And suppose its speed becomes this 20 meter per second which was there earlier. After application of force, suppose it has become how much? It has become 10 meter per second. And if you continue applying, you may stop also after some time. So your force is reducing the speed of the cart. Now, let's again apply the force in the opposite direction. Cart is coming from that side with a speed of 20 meter per second, and again you are applying same 4 Newton of force on the cart, but this time you have applied in the opposite direction. That means you are just, it is moving like that and you are pushing like this. So what will happen? That means, I mean to say that the cart is moving like this. The cart is moving like this. This is the cart. It is moving with a speed of 20 meter per second and you have applied a force of 4 Newton. What will happen? Will its speed will decrease or increase? Obviously, it will increase. And when it will increase, suppose it becomes 30 meter per second. And if you continue to apply this force, then it may increase even more also. So my question is that, in both the cases, the cart was same. This was the cart. Cart was same. It was moving initially with a speed of 20 meter per second. But in this case, you applied force in this direction. Force. How much? That is force equals to 4 Newton. And for the same time you applied. Suppose for time t you applied. But what you found? The results are different. Why result is different and everything is same? Everything is not same. Then what is different? Obviously the direction of application of force is different. So what does it indicate? It indicates that force depends on direction. Force has to do something with the direction. And that's why result is different. Yes. And so we can say force is a vector quantity. And when you are mentioning about force, you must mention it is acting in which direction. So if you want to mention the force, then you have to mention the magnitude as well as direction. Suppose towards north. 4 Newton towards north. This is the proper way to express the force, because it's a vector quantity. So it has got magnitude as well as direction. One more thing. Suppose a force is acting. These vector quantities are represented by a arrow. The length of the arrow gives the magnitude and the arrowhead gives the direction. Suppose there is a force of 3 Newton acting like this, and a force of suppose 4 Newton is acting like this on the same body. This is the body. Now, what is the total force acting on this body? If you are using simple algebra, you can say, sir, it is 4 plus 3, that is 7 Newton. No, this is wrong. Because in the definition we have mentioned, it is going to use the vector algebra. And vector algebra is that algebra which you have not studied till date. And we don't require also in class 9, small one we require. So you have to find this one. But you know Pythagoras theorem. This is 4, this is 3. What will be this? This is 4 square plus 3 square. Square root of 4 square plus 3 square. And 4 square is how much? 16 plus 9. And that is how much? 25. And that is how much? 5 Newton. So total force acting on this body is how much? 5 Newton. Okay. And that is acting in which direction? Somewhere here, in between. neither this way nor this way. It is total force is acting this way. So you cannot use simple arithmetic, and it has magnitude and direction both, and that's why it is called vector quantities. Vector quantities are denoted by an arrow over its head like this. If you are putting this, that means you are denoting a vector quantity, and you have to write magnitude as well as direction. Suppose you don't want like this, you can write like this, because here magnitude and direction both are there. But if you don't want to write the direction, then you can write like this, only magnitude. Okay. So this is all about the vector quantities and scalar quantities. Okay. Next topic is state of rest. Now the question comes, when we can say that the body is at rest? First write the definition. When a body does not changes its position, with respect to its immediate surrounding with the passage of time, then the body is said to be at rest. Full stop. For example, the green board of my class is at rest with respect to my classroom. The window of my class is at rest with respect to my classroom. That's all. Now see, what does this definition means actually? See, suppose suppose I'm standing over here. Suppose my distance with this wall is suppose 1 feet. Okay, from this wall suppose it is 7 feet. 1 feet. Okay, from this wall it is 1 feet. Okay, I'm standing here. From this wall it is 7 feet. Okay, from the front wall it is suppose 10 feet, and from back wall it is 0 feet. From the top, that is roof, let it be 5 feet, and I'm on the ground, so it is again 0 feet. So my position is this. From the left side wall, on my left side, actually I am away from the wall by 1 feet. On my right side, I am away from the wall by 7 feet. On my front, the wall is 10 feet away from me, or I am away from the front wall by 10 feet. Back wall, it is very near to me, it is 0 feet almost. The roof is 5 feet high from my head, and this floor, I am standing on that, so 0 feet. So that is my position. And if this position remains as it is with the passing time, suppose you observed me at 10 a.m. and I was at this position. You observed me at 10:05 a.m. and I was in the same position. 5:15, 5:20, 10, 10:05, 10:10, 10:20, 10:30, and you observed I'm over there only, and position is same. Then you can say that I'm at rest. But you have found that at 10, 10, 10, that is 10 a.m. This is hour, this is minute, and this is second. I was at this position, but at 10, 10, 11, you found that my position is changed. Okay, how it is changed? This has become 7.5 feet and this has become 0.5 feet. That means I moved little bit towards my left. See, that's why this distance decreased and that distance increased. So my position has changed at this time. At the interval of 1 second only, my position changed. And when my position changed, then I'm not at rest. So for being rest, what is required? With the immediate surrounding, the position of the body must not change with the passing time. Okay. Now, while giving the example of state of rest, I told you that the window of my class is at rest with respect to my classroom. So can it be at motion also? Yes. Suppose your friend is at moon, and from there using a telescope he is observing your window of your class. So what he or she will feel? Obviously, he or she will find that your window is in motion because earth is moving, and when earth is moving, then window is also on the earth only, so it will be in motion. So it depends with respect to which place you are talking, and that place is called the reference frame. Okay, so reference frame is very, very important, otherwise it will lead to wrong statement. Now, what is state of motion? At the definition, when a body changes its position with respect to its immediate surrounding with the passage of time, then the body is said to be in motion. The example already I have given, I change my position and then with the passage of time, so you can say, oh, this body is in motion. So that is all about the rest and motion. Suppose both you and your friend, both Mr. X and Mr. Y, both are sitting in an AC compartment, two-tier compartment or first class compartment of a train together, just beside each other, and you are talking. So you can say, with respect to you, your friend is at rest, and with respect to your friend, you are at rest. But at the same time, suppose both are there in different trains, and the one train is crossing the other. So what will happen? With respect to Mr. X, Mr. Y is moving ahead, suppose. So with respect to Mr. X, Mr. Y is in motion, and he is moving in the forward direction. But if Mr. Y will look to Mr. X, Mr. Y's train is crossing the Mr. X train, so Mr. Y will look towards Mr. X. He will feel that Mr. X is going in the backward direction. So with respect to Mr. Y, Mr. X is in motion, but direction of motion is different. So motion is actually a relative thing about rest and motion. Okay.